Good day again, everyone, and welcome to our feature webinar presentation this week, an application highlight on battery thermal management and optimizing the use and application of phase change materials for thermal energy storage and cooling purposes. My name is Adam Harris. I'm the Managing Director for C-Therm Technologies. C-Therm is a specialist in measuring thermal conductivity and related thermal physical properties. With me today is Sarah Ackerman. Sarah is the lead of Thermal Analysis Labs, which provides a lot of contract testing and consultancy services to a broad base of industries where issues of thermal management or heat transfer are a paramount concern. So this afternoon we're going to be highlighting some work recently published on use of a C-Therm TCI thermal conductivity analyzer and looking at the characterization of some phase change materials. We've done a lot of work in PCMs over the past 5 years. A main issue with the PCMs is certainly looking at the improvement to the thermal conductivity is a means of improving their overall performance, whether it's from a variety of application perspectives. Today we're focused on battery thermal management, but I think Sarah will talk a little bit about as we go through some of the other applications for PCMs that we've done work with in textiles and incorporated into the materials of construction and insulation and housing, and really a interesting material group to be working with for its broad purpose and use. Today's webinar presentation is being recorded. We should run approximately 45 to 50 minutes, and we will be uploading the presentation on our website shortly thereafter. We have muted the telephone lines to preserve the audio quality of the recording, but we will open up the lines at the end of the presentation for a Q&A session. So thank you again, everyone, for joining us on the call today. We hope you find it of interest, and without too much further ado, let's get started. So I want to just first provide a little bit of further background on C-Therm Technologies. We're a Canadian company. I see a number of folks on the line who we've worked with previously. I also see a number of folks who are perhaps less familiar with us. So C-Therm Technologies is a niche specialist. In terms of thermal instrumentation, we provide a pretty narrow range of equipment. What we do very, very well. In fact, we're the best in the world at measuring thermal conductivity and related thermal properties via contact-based transient methods. Our core technology is based on a one-sided interfacial sensor that you see pictured on the slide. This technology platform has won us a number of awards internationally and nationally for innovation in terms of the technical progress that we've made in making these types of measurements simpler and easier to administer, accelerating research in a laboratory environment, but also, because it's a fast one-sided technique, making it easier to migrate these types of platforms into quality control and production monitoring environments. Internationally, we've won the R&D 100 award, which previous winners include developers of anti-lock brakes, the automated banking machine, smartphone. It puts us in a pretty prestigious class of company in terms of technical innovation. And nationally here in Canada, we've won the top award for innovation in the country, the Manning Innovation Award. That was awarded to the original inventor of the technology, Dr. Nancy Mathis. That innovation is embodied in a one-sided interfacial sensor, which we'll describe further in the presentation, but is called the Modified Transient Plane Source, or MTPS for short. So in terms of understanding what C-Therm does, we are experts in thermal conductivity, and the product that we're going to be really talking a lot about today is the TCI thermal conductivity analyzer, which employs the MTPS sensor as its primary option for measuring thermal conductivity. That's what's featured in the work that Sarah is going to be presenting on the application side as it relates to measuring PCMs and how they're used in a cooling application in batteries. We've got thousands of clients around the world. You can see a few of them listed here. I will also just put a short little plug-in for our newer product line in dilatometry, measuring the thermal expansion or related dilatometry applications. We won't talk much about dilatometry in today's presentation, but there is a nice little option to parcel these two systems together. They use the same controller system, and so there's some economies in bundling those two together. Potential savings of upwards of 35% if thermal conductivity and dilatometry is of interest. But we won't talk too much more about dilatometry today. If you would like more information on our dilatometers, just put it in the chat box and we'd be happy to follow up with you. So I mentioned some of our clients earlier, but this just gives a quick snapshot of us and our global presence. So thousands of clients around the world, including groups like 3M, Samsung, Henkel, Adidas, etc. We have a global distribution network where we've got distributors and partners in 50 plus countries around the world. We're a member of the Cartmel group of companies. And this slide's a bit outdated, but we have thousands of clients around the world. So that gives you a little bit of idea of our base. A nice little testimonial we like to work in here. And if you're interested in some of the other client perspective, there is a page on our website dedicated to client testimonials. We believe our best form of marketing is a happy client, and we're very happy to share that perspective. This is a nice quote from Dr. Enrique Jackson at NASA. He comments that we purchased the C-Therm TCI thermal conductivity analyzer after seeing a demo of how fast and easy it is to operate. The instrument provides unequivocal results and provides the flexibility to test powders and liquids. In terms of our satisfaction, he gave us a 10 out of 10, extremely satisfied. So just a nice reflection on the quality of the solution we provide for measuring thermal conductivity. And one thing I really do want to emphasize and touch on here is this application included liquids. And when we talk about instrument selection for thermal conductivity of phase change materials, it's the dual phases that really I think differentiates the C-Therm TCI as an ideal solution and being able to test both the solid and liquid states. There's a lot of different choices in analytical instrumentation for thermal conductivity. Some do very well on solids, some do better on liquids. The TCI is really the only one that transitions effectively between the two, and so it makes it an ideal solution for measuring phase change materials. So this is a close-up view of the product. It can also be configured with a needle TLS sensor for transient line source. TLS is used more for stickier situations. It's sheathed in stainless steel, so it's a very robust sensor. It's not quite as sensitive as the MTPS sensor, and it's a little bit more limited in terms of the range, but it's a really good option when we're testing polymer melts or materials that may bond to the sensor, and it provides a nice complement to the MTPS on the same overall TCI platform. With the system, we're measuring two thermal properties primarily. The first is thermal conductivity. This is a fundamental heat transfer property. It's what 95% of our clients are interested in measuring. So this provides a very effective direct solution for measuring thermal conductivity. We do also measure another thermal property called thermal effusivity. Effusivity is defined as the square root of the thermal conductivity, density, and heat capacity. There are a couple of reasons why thermal effusivity is broadly of interest. It is more of a bit more obscure as a measurement, certainly not as common as effusivity. But there's a couple of reasons that it is becoming more and more popular. The first is when you're able to obtain both accurate direct thermal conductivity measurement and effusivity, you can see based on this equation, if you know the density of your material, you can easily approximate the heat capacity for the sample. This would be an indirect path for determining heat capacity. if you came to us and said, Sarah or Adam, I really don't care about thermal conductivity, I only want heat capacity, we would steer you more in the direction of a DSC as a more accurate means of measuring heat capacity. But sometimes with limited time, limited budget, it's nice to be able to derive additional thermophysical property data on our sample. So the indirect ability to determine heat capacity is sometimes a nice value add. The other reason that effusivity is of interest really relates to quantifying touch properties, sometimes described as touch haptics or surface haptics of a material. Thermal effusivity can also be called thermal inertia, but it really defines whether a material feels warm or cool to the touch. So real quick, this is a correlation study done at the University College of London in the UK, looking at the perceived coldness as tested with a human test panel, 5 being on the upper end scale of being very cold, 0 being very warm. And you can see that there's a very nice correlation there, that as the higher the value in terms of effusivity, the colder the perception of it. Just pausing there for a quick second and thinking about why would we care about that. There's a lot of applications where the sense of touch matters, mostly in consumer goods. In textiles, it's become very, very important. There is an overlap with where phase change materials are increasingly used in textiles for heating and for cooling purposes. And what the material feels like from the human responses perspective is something that's very beneficial to being able to quantify. Of course, you could use a human test panel, but the problem with human test panels is that they can certainly vary depending on the group. There's natural biases that become an issue, difficult to get a good agreement between different groups administering the same test. So an instrumentation that can quantify that feeling of warmth or cool provides a significant benefit to a range of application in consumer goods and textiles. I won't go into this part too much further. Similarly, if you are working with phase change materials in textiles, there's a lot more that we could share with you, and I'd encourage you just to put a quick note in the chat box that you're interested in PCM textiles, and we'd be happy to follow up with you accordingly. I will also ask Sarah to just comment a little bit during her section on how effusivity can additionally be used in looking at phase change materials. There was some interesting work that I know she presented earlier. I don't know if it's in the scope of this presentation, but I'll ask maybe at the end just to maybe speak a little bit about where effusivity can also be used in PCMs. Okay. Real quick, I do want to take you through the theory of operation to the method just before we transition this over to Sarah on the application side. The first is to understand what the technique can and can't do. And when I describe the technique, I am referring to the Modified Transient Plane Source method. Again, the method is going to be highlighted in today's application work. So the technique is capable of measuring effectively the thermal conductivity up to 500 watts per meter Kelvin. That covers a very broad range of materials. Copper, for example, is around 410, 420 watts per meter Kelvin. Most polymers are under 1 watt per meter Kelvin, and insulation is typically under 0.1. So just to give you something to relate to if you're not working a lot in thermal conductivity, this is covering a very broad spectrum of materials. The temperature range is typically minus 50 to 200 degrees C for a sensor. That means the sensor can withstand those operating conditions. The sensor doesn't heat or cool anything to that temperature range. It's more of a passive sensor, but is very flexible in being able to be placed in different operating environments. That can, for example, mean a furnace, thermal chamber, humidity chamber. We have clients in the nuclear field working in hot boxes, different radiated environments, high pressure cells, etc. There is an option as well to extend the temperature limits of the sensor up to 500 degrees C in certain application areas. The accuracy is better than 5%, and the precision is an industry-leading better than 1%. This is by far the most precise technique in terms of the reproducibility and consistency to the data. Conforms to a number of ASTM standards depending on how it's configured. D7984 with the MTPS, and D5334 and D5930 with the needle TLS sensor. Okay, so in understanding what it can and can't do, let's talk a little bit about the basic theory of the measurement. So first off, it's a contact-based measurement. So whatever we're testing is placed in direct contact with the active area of the sensor, which is about the size of a US nickel coin. About 18 millimeters in diameter is the active surface area. If we're testing a liquid or something that's going to turn into a liquid, we have a small cell that sits over top of the sensor and provides a place to localize the sample and presenting it to the sensor. I think I've got some pictures further on to illustrate what that looks like. In zooming in a little bit more on the active component to the sensor chip, the most important part of the system, it's made out of a thin piece of alumina as a substrate, and we deposited a platinum alloy in a coil formation. There are two circuits to the sensor. One is the coil and the other is the guard ring. We heat both electrically, kind of like you would an electric stovetop, and applying current. But at the same time with the sensor coil, we're also monitoring the temperature change over time. So essentially what we're doing is we're putting a fixed amount of energy by electrical heating into the sensor, and at the same time we're monitoring the change in temperature over time. It's that change in temperature over time, plotted as a slope, that is inversely proportional to the thermal conductivity or thermal effusivity of the material. So to show you what that looks like in terms of the raw data, this illustrates what a result would look like. And in this example on the screen, we actually have two different results overlaid just to illustrate the point and differences between a result in testing an insulating material versus a conductive material. So the raw data is plotted as a voltage drop over the square root of time. I find this a lot easier to relate to if we just think of it as temperature change over time. That voltage drop is calibrated to temperature change. Okay, so we use it essentially as like a thermocouple in monitoring the temperature change over time. You'll notice the start time to the calculation of the slope here, this perforated line. This is one of the techniques we apply to reduce any effect of contact resistance. So this is a transient-based measurement. So the thermal transient that we're creating and electrically heating the coil, we need to provide that sufficient time to penetrate the boundary condition of the sample. Doesn't matter how good the contact, there's always going to be some resistance there in transitioning from the sensor to within the sample's boundary conditions. There is, for example, a dielectric coating over the active sensor, which electrically isolates the sensor and makes it suitable for testing both electrically conductive materials as well as non-electrically conductive materials. So we chop off the first third of the data roughly, and we're looking at the slope of the back two-thirds of the measurement. The steeper the slope change, so the faster that temperature is increasing over time, the lower the effective thermal conductivity of the sample. If we have a really good heat sink on the sensor, we'll see a more negligible rise in temperature change over time, because that heat energy that we're applying is being transported away so effectively due to the high thermal conductivity of the sample material. So in the case of the metal, you can think of like a nice piece of copper that's really doing a good job of dissipating that heat. So I wanted to give that information to you just so you have some familiarity and comfort with the principles involved in measuring thermal conductivity the way we do. I think it's also really important to just emphasize you don't have to interpret any of those voltage time plots. One of the things we've really aimed for from the beginning is to simplify thermal conductivity, to make it as accessible as possible to the broadest range of user profiles. So whether you're a trained PhD or whether you're a technician operating on a production line and just looking to do QC testing, The objective was to make this as simple as a one-touch push of a button to obtain thermal conductivity. And we've done a very good job of that. And so what we report in the software is the tabular results for the thermal effusivity, the thermal conductivity, the temperature data, all of which is very easy to export to Excel. Makes it really fast and easy and much more reproducible between different users, different facilities, different groups operating globally to get an apples-to-apples comparison in terms of the effective thermal conductivity of their materials, whether they're solid, liquid, powder, or paste. So we're often asked for, how does this method correlate with other techniques, or how do you prove the efficacy or effectiveness, rather, of your method? The best way to verify the performance of any thermal conductivity instrument is to go out and source a really good standard reference material, preferably from a certified source such as NIST or NPL. So NIST, the National Institute of Standards and Technology, produces a range of materials which have certified values in terms of their thermal conductivity. In the UK, there's also the National Physical Laboratory, which does an excellent job as well of producing these types of materials. In this case, the example given is EPS, so it's an insulation material, expanded polystyrene, has a conductivity of around 0.0337 watts per meter Kelvin. And that stated value is presented on the certificate with the purchase sample, is the bold line that goes across the screen there. Now the dashed lines on the top and bottom represent the uncertainty to that value. So on the same certificate, it will say that it has a conductivity of X plus or minus Y. And that uncertainty is typically in the range of 2 to 3% for most certified standard reference materials. I think in this case it's about 2.2%. The dots represent the measured value with the MTPS sensor that you see with the setup here. Now the weight on top of this sample, which is sitting on top of the sensor, the weight is just to ensure you get a good contact between the sample and sensor. With lighter samples, we don't want them to float too much on the sensor rather. We want them to have a good intimate contact in optimizing that effective transient to penetrate into the sample's boundary conditions. These results are excellent. They're within the 2% uncertainty. Our spec is better than 5%, so just one example of many in terms of the performance of the system. If you go on our website, you can look up different correlation papers. I know there's a really good one on stainless steel as well. And other papers comparing to other alternative methods, including TPS, TLS, guarded hot plates, laser flash, lots of other techniques out there for measuring thermal conductivity, all with their own pros and cons, but plenty of correlation work done in this space as well. All right, just before I pass this on, I just wanted to highlight a couple of the accessories and unique capabilities offered with this platform. With testing phase change materials, of course, you do get into a liquid state, and the addition of the fluid cell is a nice one. It just sits on top of the sensor. There's an O-ring embedded in it, which is replaceable underneath. And provides a nice way of testing fluids. When you're testing fluids, one of the impacts or things you want to be careful with is impact of convection. And there's a few different ways we optimize for testing liquids, particularly lower viscosity liquids where convection is a greater concern. One is reducing the volume, and that's one of the things this accessory does a nice job of. But you also want to keep a very low power density to the measurement and also a very short test time to the measurement. With some alternative techniques for measuring conductivity of fluids and semi-solids, the longer test time can really start to creep up as an issue in terms of driving higher reported values that are really more of a result of a bias related to convection. So just something to watch out for. Sarah is extremely knowledgeable on that, much more in tune with those dynamics than myself. So if you have any questions, that's a good one for Sarah. All right, lastly, just a couple of the other accessories to think about. The thermal chamber is something that is necessary in looking at phase change materials where you need a controlled heating of the sample. So we recommend the 10E Junior thermal chamber and can provide it as an accessory. We do also have a really cool line of high pressure cells for both solid and liquids. In process safety, in fields related to oil and gas, exploration, extraction, etc. Understanding the thermal properties under elevated pressure conditions can be something that's quite important. And then, of course, I already talked about the TLS sensor, so I won't do much more there. I think this is a great point for me maybe to hand this off to Sarah. So Sarah, thank you very much for joining us today. I'll ask you to take us through a little bit of the work that we're featuring here from one of our clients and looking at application in batteries.
Thanks, Adam. So, while we are just ahead of talking about the work that's being presented here, I'm going to talk a little bit about battery thermal management in particular and how batteries work, just to make sure everyone's kind of on the same page. Some of you I know personally and should be very good experts, and we have some other people who are a bit newer to the field, so I figure I'll give everybody the same general footing. So batteries in general are devices that were first discovered back in the 1700s, and they are basically engineered to convert chemical energy stored either in chemical bonds or in the lack of a chemical bond when you're dealing with a pure metal into electrical energy, and vice versa sometimes if you're dealing with a rechargeable battery. And they use a series of electrochemical cells connected electronically in series to achieve a desired potential across the battery cell. They are a great device, and they're completely necessary for modern life as we know it. But they do come with a few technical problems, and even though they've been around for several hundred years, there's always room for improvement. One of the problems is that most batteries require a relatively narrow temperature range to achieve the best performance. If they get too low for it, then they can have problems with self-discharge. And if you overheat it, you can lead to performance troubles, shortening the lifespan of the battery. In most battery types, overheating will cause damage to the cell or to the device that's using the cell. And then in the extreme case, you have lithium-ion batteries, which can actually explode if they overheat. So there's been a bunch of videos and news stories about this problem around lithium-ion batteries, and it's actually why a lot of lithium-ion battery devices are either restricted or prohibited from air travel. The explosion risk with these batteries poses both injury hazard to the end user and also fire hazards. So really, thermal management is key, especially with this type of battery, to avoid any potential hazards associated with overheating. I mean, overheating is not desirable in any battery, but it's especially critical to avoid in the case of a lithium-ion battery. So one of the strategies to address that, there are a few others, such as switching to alternative cells that are being explored, but one of the current strategies to address it is through the design of thermal management systems. So thermal management systems in general combine several different aspects, including user education, cell design, cell packing with coolants or thermal interface materials, and passive or active or both types of cooling in general. And then design of an intelligent system is the next level, whereby the system itself can detect if it's overheating and initiate a safety procedure like an emergency shutdown. So many people who've had the experience of having their computer shut off on them on a hot day have experienced that kind of intelligent system safety procedure. So where PCMs come in is right in this center part in the packing of the battery cells. But there's a bunch of other factors that come into the thermal management. So looking at the PCMs in particular, they're very promising materials as far as battery thermal management is concerned, and there's a few particularly attractive qualities of PCMs. The first of which is that they tend to have a very high heat capacity because you're exploiting that enthalpy of phase change, which is typically at least one, sometimes two or three orders of magnitude larger than a mass-specific heat capacity for a traditional type of cooling fluid. They also tend to be very chemically and physically stable. And if you tune the composition of the phase change material, you can usually tune the phase change temperature so you can tailor your PCM's properties to your desired end-use operation. But there is one key problem with the PCMs as far as battery thermal management is concerned, and that is that they tend to suffer from having a very low thermal conductivity. So that is something that does need to be addressed because their thermal conductivity is only on the order of about 0.2 to 0.3 watts per meter Kelvin in the solid phase. In the liquid phase, thermal conductivity is not as important because heat transfer in liquids tends to be dominated by convection effects, and it's the physical motion of the fluid which transfers the heat from one area to another. But in solids, you don't have the option of physically transferring your heat transfer medium from one area to another in order to move the heat. The only way that the heat can move is through thermal conduction. So if there's a very low thermal conductivity on a material that's supposed to act as a heat sink, that's a significant problem from a thermal management point of view. So moving into phase change materials more generally, as the phase change material works, it goes through multiple physical states or physical phases. So typically you'll start with a phase change material in the solid state, and as heat is generated by whatever process you're looking to cool, sometimes it's a person's body if you're using an ice pack on an injury as an example, the temperature of the phase change material is going to rise, and the phase change material will absorb that energy associated with the temperature increase. As it absorbs the heat energy, it's going to liquefy or melt, which leads to the phase change material being in the liquid state. Eventually, if there's no longer a heat source around, it will start to cool off and transfer heat back to the environment, and as that happens, it's going to re-solidify. So this is very much a cyclic operation. And the best phase change materials have cycle lives that can be measured in thousands of cycles. So they can be a very long-lasting and robust solution for heat management systems if you can tune the thermal conductivity. Phase change materials have a lot more applications than just looking at batteries in particular. So they're used, as Adam was talking about earlier, in housing construction. One group was producing some very interesting work a few months back about installing phase change materials in floor panels in basements so that the floor wouldn't get so uncomfortably cold when you walk on it in the winter. They're also used in the electronics, not just in batteries, but also as coolants on PCB boards to help remove heat from components that are at risk of overheating. They can be used in footwear to help people keep their feet warm in cold weather. And a lot of work is done in textiles in general, so bedding, seating, apparel, those sorts of things, with various phase change material treatments and coatings to help optimize human comfort in the use of the textile product. And one of the most common places where they're used is in thermal energy storage. So thermal energy storage has a couple of different ways that it can be done. One is through sensible heat storage, through the specific heat of a material. There's also thermochemical storage, like in salt dissolution packs, or by taking advantage of reversible chemical reactions. But the biggest place where thermal energy storage is performed is in the field of phase change materials using latent heat energy storage. So looking at latent heat energy storage, exploits a phase change of a material. And for those of you who are new to heat transfer, the reason why latent heat is called latent is because it's kind of hidden from the sensor or whatever you would be using to observe the process. So if you look at this, you've got the solid phase, and as the solid heats up, its temperature is going to increase. So that traditionally is called sensible heat, where as more heat is pumped into the material, you can observe how much heat is being put into the material by measuring its temperature. So you can sense how much heat is in that material, hence why it's called sensible. Latent heat is called that because even as you pump more and more heat in during the phase change, the temperature doesn't rise very much. At most it might rise 1 or 2 degrees. So it's kind of hidden. And then after the phase change is complete, the temperature will start rising as you add more and more heat into the material again. So that all brings us into this work by the international group that developed these PCM thermal management systems for lithium-ion batteries. So this was work out of the University of Windsor up here in Canada, in Ontario, and also in partnership with Wayne State University in Michigan in the USA, and published in Advanced Science News. So looking at some of the barriers of lithium-ion batteries for widespread commercial use, lithium-ion batteries are used commercially in some applications, but they can't be introduced very widely owing to a number of factors. One of the biggest ones is safety. I mean, most people who've been watching the news this year have seen those videos last Christmas, for example, of the exploding scooters and exploding cell phones and various other problems. Those are all associated with lithium-ion batteries. So there are significant safety concerns regarding them that need to be addressed. There's also cost related to the cycle life. They tend to have a lower cycle life than some of the other options out there, like nickel-based recyclable batteries. And in lower temperatures, they can have issues with self-discharging. But the biggest challenge is associated with thermal effects in the battery, including overcharging and overheating, both of which can result in a runaway reaction inside of the battery, which eventually leads to an explosion. So the approach to this that is being taken in this work is to design a method of moderating the temperature of the battery cell. And like with most thermal management systems, this takes a combination of several different approaches, including air cooling with fans and liquid cooling, as well as passive cooling, such as the use of a phase change material. So PCMs have the advantage of being uniform in terms of their cooling effect. They're physically compact, and they tend to have a lower cost of operation compared with the active cooling approaches. But there are a few challenges. So for example, during very aggressive operation of a device, they might be insufficient in terms of their kinetics and their heat capacity to fully cool a material or a battery cell. They also have a relatively unfavorable thermal inertia. So thermal inertia is a property related to the thermal effusivity of a material, and it basically quantifies how quickly phase change material can be cycled. So this is relating to some of that work using the thermal effusivity. Basically, the thermal effusivity is directly proportional to the thermal inertia, and if you measure the thermal effusivity during a phase change, the peak thermal effusivity value is basically the thermal inertia associated with the battery. So if you have an unfavorable thermal inertia, the problem that causes is that the kinetics of the battery cycling of the system cycling are too slow, and therefore it can't get rid of heat, excess heat to the environment and resolidify quickly to be ready for the next operation cycle. On the other hand, neither can it absorb heat very quickly if the battery cell is overheating suddenly. So that's a little bit beyond the scope of this work, but we do have a blog post, and I think we touched on it in a previous webinar on phase change materials. So please feel free to check out our recordings of previous webinars on the website if you want some more information on that, or ask about it in the question and answer period after the webinar. And then the biggest one, and the one that we're addressing in this webinar, is that they have an issue of having low thermal conductivity. As I was mentioning earlier, most phase change materials have a thermal conductivity in the solid phase of around 0.2 to 0.3 watts per meter Kelvin, and that's a real challenge in terms of operating a coolant system. So the proposed solution that the researchers took to address this issue was to enhance the solid phase thermal conductivity of the phase change material through the use of carbon nanoparticles to help improve the thermal conductivity in the solid phase and therefore improve the rate of heat rejection from the system. And then they also wanted to improve the rate of heat release, and they tried that by improving the airflow through the system to help cool the phase change materials more quickly. The results of this work can be seen in this slide. So you can see we have the thermal conductivity here on the y-axis and temperature here on the x-axis. So the pure thermal PCM material is seen right here in this blue line, and the 5% loading by weight percent of the nanoparticle wax material is seen here, and then the 10% loading is up here in red. So you've got black or purple, I think. Purple squares gives you the 5%, red circles is the 10%, and the blue diamonds give the pure wax material. And you can see here that in the solid, the thermal conductivity is about 0.25 watts per meter Kelvin for this particular paraffin. And a fourfold increase is achieved by adding 5 weight percent of nanoparticles. And then if you double that weight percent, you actually get a much greater increase than just a doubling of the thermal conductivity relative to the 5%. So there seems to be a nonlinear relationship between the weight percent added and the total improvement on the thermal conductivity. Addition of nanoparticles to the PCM did have an effect on the liquid phase, but this effect was very minor. Going from the pure paraffin wax in the liquid phase to the 10 weight percent nanocomposite only gave an improvement in the liquid phase from 0.16 watt per meter Kelvin up to 0.18. So that's really only about at most 10%, and this is pretty typical of what you would expect with a nanofluid. In fluids, the heat transfer does tend to be dominated by convection effects, though. So the lack of huge improvement in the liquid phase is not a terribly big deal, because the heat transfer in the liquid phase is mainly achieved through convection anyway. And a study was done studying the layer thickness of the phase change material and its effect on the average temperature difference achieved relative to a system which had no treatment. So you can see these plots here show that the thicker the layer was, the better the performance of the system was in terms of absorbing the heat, which you would expect that because you have more of a more heat capacity to absorb the heat from the battery material. These two simulations show the overall improvement of the performance using the pure wax phase change material versus the nanocomposite wax with 10 weight % nanoparticles added at the end of a driving cycle. So you can see how much more uniform and how much cooler the nanoparticle composite phase change material is able to keep the battery panels. And this would lead to more stable and safer operation of the lithium-ion battery in practice. So in terms of the optimal conditions, a 2 millimeter thick layer of 10% weight loading can maintain the temperature about 1.9 degrees lower compared with the pure paraffin. So in conclusion, in addition to identifying those optimal conditions, this paper really highlights how the MTPS sensor of the TCI thermal conductivity analyzer really provides the optimal method for analyzing the phase change materials, because the researchers who did this work were able to analyze their material without having to worry about the risk of introducing convection errors, because the MTPS method uses a very short test time of 1 second. Other methods that might use longer test times run into the issue of convection. So we've done a lot of ANSYS simulations of liquid systems. They're available on the website, and the cliff notes of those simulations is that anything after about 3 to 4 seconds with less viscous fluids and 7 seconds with more viscous fluids, you're going to run into an issue where you're going to get thermal convection. And if you're using a method that has just a 2-point analysis method like transient hot water or transient line source, and you're using a longer test time than those limits, you're going to overestimate your thermal conductivity, because your data is not just governed by the conduction through the liquid, it's also governed by convection. It's also affected by convection. So in order to avoid that overestimation of the thermal conductivity and to make sure you've got a real and accurate and realistic value for your fluid's thermal conductivity, you really need to keep that test time short, which is what this method does. It also helps improve the repeatability of the test results, as it has an easy setup and fast operation. So it's very easy to train people and bring them up to speed on the proper operation of the device. And it also gives an accurate test result, because, as I said, the test method uses a short enough test time that you don't have to worry about that you're running into convection effects on your data. So for more examples of how the method can be used, please feel free to check out our other phase change material webinars, or ask us some questions either in the chat box if you want to, if you don't feel comfortable asking on the question and answer period, or you can ask us in the Q&A period, which is coming up shortly. At this point, I'll hand things back over to Adam, and he can close things off.
Great. Well, wonderful presentation, Sarah. Thank you very much. And this really does bring us to the end of the formal part of our presentation. Shortly, we will unmute the telephone line. Let me just take care of a couple of quick items first. I do want to point out some resources on our website. As we mentioned earlier, we are recording today's webinar presentation, and it will be posted online. So I know some folks who registered were expressing that they would have difficulty with the scheduling, and so same for any of your colleagues. If you know of somebody that might be of interest, let us know. We'd be happy to send them a link to the recording. There's also a technical library there, which I think Sarah mentioned, pointing out some of the resources there, but there's a number of application papers that speak to use of the technology. I think there's now 400 or 500 different papers citing reference to the MTPS method. And then all the normal stuff that you would expect on our website. We've got some demo videos and a blog where we feature different applications that are novel or interesting. But it is a pretty substantial technical resource, so I do just like to point it out. Lastly, let me just thank you again. We really enjoy the opportunity to share with you some of the work we're doing in thermal conductivity characterization and highlight how we can support clients in a range of applications from phase change materials, batteries, textiles, polymer composites, etc. But it's great to be able to get this opportunity to share with you some of that information. I know your time is valuable, and anyways, very much appreciate you joining us online today. So that said, let me stop the recording and bring the formal part of our presentation to a close. And in the process, we'll also open up the line for our Q&A session. Hold the line, please.